Hi, last day. So, I don't know if today is, I would say a relaxing lecture, but I suppose that's in the eye of the beholder. No math today, just orbitals. We'll do some qualitative orbital. I want to do one more example, kind of application of molecular orbitals here. And there's a really logical choice. There's many logical choices. We did aromaticity yesterday. Of course, that's the classic. But aromaticity is kind of an old school idea. Let's do something a little more modern. And in fact, this is what we're going to talk about today is kind of the one Nobel Prize winning work that is, or the first Nobel Prize winning work that's powered as for an application that's powered by molecular orbital theory. Right? So what we're going to talk about today won the Nobel Prize in 1981 by a duo of scientists, Roald Hoffmann, who I've actually had lunch with before. He is a Holocaust survivor, works at Cornell, is a theorist, kind of one of the last remaining kind of chemists in theoretical sense. Kind of his interest is chemical bonding, the fundamentals of chemistry. So he kind of comes from an old-fashioned world of theory. Still in his 90s, still doing research today at Cornell. Another guy that won this is Kenichi Fukui, who's another a Japanese theorist calculation. We won't talk anything about Fukui's implementation of this work. He kind of took what Hoffmann did and created a program to do it. He's kind of the guy that does the calculations, if you will. Hoffmann is the thinker, and Fukui is the guy that come up with a quantitative way to do this analysis. And it wasn't awarded to the third person, who's actually the other creator of this theory, because he died in '79. Is my hero, Robert Woodward, who is a chemist, a synthetic chemist at Harvard. He died in 1979 because he smoked 3 packs a day and drank liquor every day in class. He was one of those guys. Very famous for, if you ever watch Woodward's lectures, you'd understand why I like him. He sits in, his lectures are like 3 hours long. He knows everything. And he gets drunk and smokes cigarettes while he does it. He's just the classic organic chemist. But he died, so he didn't get the Nobel Prize. No, dead people can't win Nobel Prizes. So he didn't get it, but he certainly deserved it. He did win a Nobel Prize for something else earlier, so this would have been a second. And the idea I want to motivate, instead of talking about specifically what these guys did, I want to motivate it with an example. Right? And this is an organic chemistry. I'll give you the title. So the title of this is what's called Conservation of Orbital Symmetry. Right? We won't really talk so much about the symmetry part, but what we'll do is we'll apply this directly to what they apply it to. I kind of want to do this in example based and discuss kind of the really simple insights of Hoffmann and Woodward in particular. And I want to motivate it with an example from organic chemistry. Well, there's a class of reactions. If you take a diene like this, that can be any length you want. Maybe we can put some R groups on it anywhere we want. Doesn't matter. And we react it with a double bond with another group like that. Again, it could be hydrogens, anything. And you put it under heat. What happens is that these two molecules add together to form a 6-member ring. And I'll do the arrows in just a second. You get a double bond here. R double prime actually goes negative, goes down like this. And let's see, what do we have next? We have an R here, and then an R prime here. All right, so what we've done is we've taken this the 4-pi electron system, the 2-pi electron system, and put them together into one big ring. This was called the Diels-Alder reaction. You might remember this from organic chemistry, Orgo 2 probably. Maybe not. Did you guys learn this in Orgo? Yeah, okay. So you've seen this before. All right, however, you might imagine, okay, well, I can do this with a diene and a double bond, so why can't I just do this instead? To form a 4-member ring in the same way. Like so. But when you do this with heat, It doesn't go. In fact, the only way to do this is to use light around 300 nanometers, or 260, ultraviolet light. Right? So the only way, meanwhile, if I do the same thing here, if I add photon, this doesn't go. Okay? So this reaction proceeds thermally. The equivalent reaction with two double bonds does it, but it goes with light, but this one doesn't go with light. Okay? And the question is why? Right? And there are a number of different types of reactions that do very similar things. And they all have a set of rules. And that's what Hoffman, Fukui, and Woodward won for, were for these rules that allow us to predict which reactions go, what kind of selectivity they have, and why this doesn't work and why this one works thermally. Okay? And they use molecular orbitals for that. Right? And it's really easy to understand it if we just draw some orbitals for these different molecules. I'll show you that to you. And if we use the idea that chemistry often is due, and what I mean by chemistry, I mean changes, chemical changes, often due to interactions of electrons in the reactants HOMO orbital with the empty orbital, the empty LUMO of the other. Or the idea is that the HOMO of one species has some electrons in it, and the LUMO of the other species provides a place to put those electrons, because it's empty. Right? I call this frontier orbital theory. Right? And there's a whole literature, whole world of study that looks to try to justify chemistry and predict chemistry by just analyzing the HOMOs and LUMOs of the reagents. Right? That's where the most labile electrons are, the most freely moving electrons are, and the LUMO is the lowest energy place to put electrons. So the way this reaction works, it's a concerted reaction. The idea is, it depends on how you look at it. There's different ways to draw the arrows. But the idea is just that the pi electrons move like this, and you form a double bond here. You destroy these two and this one, and you form one on this other side here. Okay, same idea. They all kind of work in this concerted way. Like that. Okay, that's how you would push the electrons in this case. But the question is why do these, physically, why does this work and this not thermally? And so we should just use frontier orbital theory, right? Look at the LUMO and the HOMO of these two species, and we should be able to predict things, and in fact we can. That's one of the great insights of Woodward and Hoffman, was that we don't really have to do anything fancy. We just have to look at where the electrons are and the easiest place to put them, and understand it geometrically, and we'll be able to figure out exactly why this goes and this doesn't. Okay. So the idea is this. We're going to have two different options. Of course, so let me go ahead and draw my diene. Again, we call this a diene because it's a di-double bond. And we're going to react it with what we call the dienophile, which is just a plain old normal double bond. Right, and I want to, again, we want to put some substituents on these. It's not that interesting just to mix these two. Again, this will go. If you put ethylene and get a diene together, they will react eventually. It's a very slow reaction. But somewhere we might want to put some groups, right? Some groups that change the electronic structure of the molecule. Obviously, we're more interested in functionalized systems. And so there's a couple different options. We could maybe, I'm going to draw this, I don't know where I'm going to put it. This is just, I'm going to put a group somewhere on the bond. Maybe we want to put an electron withdrawing group here. And maybe we want to put on one of the bonds here, I guess it doesn't matter, they're the same, so I won't draw it that way, an electron donating group here. Or we could do it the other way around. Right? We could also have electron donating group on this side and electron withdrawing group on this side. All right, we'll look at both. We'll look at both cases, and the analysis will be the same in either way. Things will just get flipped, as we'll see in a second. And so just as some examples of some EDGs and some EWGs, electron withdrawing groups, some classic ones are trifluoromethyl. It's a great one. Esters and esters and acids is another good one. And my favorite, cyanide. It's a great electron withdrawing group. And donating groups can be the classic in organic chemistry is the nitro group, the NO2 group. That's an extremely electron donating and donates a lot of electrons in. And another one is an aldehyde group as well. There's some other ones. Right, it doesn't matter so much. But what I want to talk about more is about the phenomenology of this idea. So the idea now is what do EDGs and withdrawing groups, donating electrons groups, do to the HOMO, LUMO of each species? Right, and there's generally generally they kind of have two different responses, one for each, and they're opposite each other. The idea is that a withdrawing group pulls electrons from the double bond, or the diene or the dienophile, whichever one. The pi, let's just call it the pi system. So EWGs pull electron density away from the pi system, which reduces the strength of the pi bond, lowering the energy of the LUMO. And I can kind of draw this figuratively. So let's imagine we have this molecule without any groups on it. All right, and its HOMO and LUMO look like this. And again, for a conjugated system, the HOMO is completely filled. And then what we're going to do is add an electron withdrawing group. And what that's going to do is effectively, I don't know how to draw it, but the idea is that it effectively kind of pulls an electron away from the double bond so that the occupation here is 2. So there's 2 electrons in this bond. And then with the electron withdrawing group, it might be more like 1.8. Right? It pulls some of the electron density away. And what that does is it reduces the amount of repulsion, and it makes the LUMO drop in energy. So the LUMO is less repelled by the HOMO. There's less bonding, so the system, the orbitals start to compress a little bit like this. So effectively what it does is that with electron withdrawing groups, EWGs, reduce the energy of the LUMO. Right. It also slightly raises the energy of the HOMO, but to a less extent because there's electrons in there and they repel each other. But effectively, it lowers the energy of the LUMO, makes that gap smaller. All right, and of course, donating groups do the opposite. Right. So if I add an donating group to my molecule, then what's going to happen is I'm going to, again, I have 2 electrons in here. Now that's all the electrons I can put into that orbital. So where are the electrons from the donating group going to go? Well, they're going to go into the LUMO, like this. And what that effectively does is increase the repulsion between the HOMO and the LUMO. And so what you end up getting is a raised HOMO energy and a raised LUMO energy like this. So the gap between the HOMO and the LUMO increases, And the HOMO energy also increases due to energy, raises energy due to electron repulsion. Okay, so the idea is, in general, electron withdrawing group lowers LUMO energy, and electron donating group raises HOMO energy. Okay, and now it's not clear why I'm referencing this, but it'll become clear when we start to analyze the Diels-Alder reaction. Okay. So I'm going to erase this for now. We'll come back to the 2 + 2 in a minute. So now the idea is that we want to apply frontier orbital theory. So what we're going to do is look at 2 cases. One, we'll put an electron donating group on the diene, anywhere, doesn't matter where. And we're going to add it to an electron poor diene. Okay? And so now what we can do is draw the HOMO and the LUMO for these. The donating group on this one, so let me write the diagram like this. We'll have diene here and dienophile over here. The HOMO of the electron of the diene is going to be high in energy. It'll be like right here, we'll say. There's 2 electrons in it. Here's our LUMO that's way high in energy. And then on this side, we have an electron withdrawing group, which lowers the energy of the LUMO for this system, and also the HOMO. Okay, and so the question is when we apply frontier orbital theory, we have 2 options. One, we can interact the HOMO with the LUMO of the other one, or we can interact the LUMO with the HOMO of the other one. Okay? All right, we have 2 options of the way the molecules are going to interact with each other. And of course, what we want are 2, in general, with molecular orbital theory, we want to combine orbitals that are close in energy together. Right? So the relevant interaction will be this interaction. The HOMO of the diene with the LUMO of the dienophile. So let's draw the HOMO and the LUMO of those 2. So again, we can take any combination we want, but this is going to be the strongest combination because they're closest in energy. So let's draw the HOMO of the diene. Now you can go back and look in your Huckel MO notes. We did butadiene in the first class, and if we didn't, then you can calculate it with Huckel MO theory. And the HOMO of this looks like this for the diene. I'm just trying to draw it like a square here. There are p orbitals on each atom. So this is the diene HOMO. And the HOMO looks like this. It changes signs in the middle. So the sign of this is the opposite of the sign of that. Notice that they're not the same on either end. And then we need to compare it to the LUMO of the dienophile, the double bond, the single double bond. And of course, that's just a double bond. There's only, when you form a double bond, you get a bonding combination, an anti-bonding combination. So the LUMO for this, for the dienophile, I'll put it right here. Has opposite signs on each one. Let me change it so that it looks like it's matched with this. Sorry. Sorry, this one should be positive and this one should be positive. Like that. Okay. So that's the LUMO of the dienophile. So what happens when these 2 molecules come together and they can interact HOMO and LUMO? Well, there's a natural way to add these together. If the LUMO kind of comes in from below, this matches this lobe, and this matches this lobe. So there's a way to combine those together. Right? I'll see if I can draw it. So when we combine those together, so again, we have our p orbitals in the back. We don't really care about those so much. And these are now going to add constructively to the ethylene, the double bond, which I draw in purple here, like so. Make sure the colors are all matched, like that. Okay, so what's happened is that I've combined these two orbitals together, and they're phase matched as they approach each other, right? You have opposite signs on the LUMO of the dienophile coming in, and that matches the ends of the HOMO of the diene, right? They can come in together and add constructively, and you get a nice bond here. You get a new bond, a new single bond here. My marker's dead. Hold on, sorry about that. So let me redraw this to make it a little cleaner. So the idea is that we're going to insert this into here, right? So this is going to kind of rotate in, and this is going to kind of rotate this way to create a new bond. So we have an outside lobe here, and an inside lobe here, like that. And these interact with the ethylene, like so. I'm just kind of going to draw that like that. So now we formed a new bond. Right? This is a new single bond. Right? So there is constructive overlap of the HOMO and the LUMO. The HOMO of the diene and the LUMO of the dienophile. Okay? Right, so that's why this works very readily, and as long as these have enough energy to overcome the barrier, right, you have to break this pi bond, if you will, to connect to here. So you have a small barrier, but there's nothing stopping this from adding into these orbitals right here to construct a new bond in the middle. I've missed, I apologize. Actually, this is 4, not, it needs to be, I've missed something here. No, that's right. Sorry, I've missed, what have I done wrong here? Is that still right? Yeah, that's still right. I apologize. Yeah, that's good. I just couldn't, I can't read properly. We have 1, 2, 3, 4, 5, 6, yeah, 6 orbitals. This is kind of kinked. This is actually should be kinked. Should be a hexagon instead. I apologize, but you get the idea. Right. So that gives us a very natural way for these to react thermally. Is that when you combine the HOMO and the LUMO together in this way, you get a constructive overlap. All right. So let's do the opposite of case, where now we have an electron donating group on the dienophile, and an electron withdrawing group on the diene. Right? It's the opposite case. So that means that what happens is that the LUMO of this decreases in energy. And the electron donating group raises the HOMO energy of this. So the HOMO for this is going to be closer to the LUMO in energy. Just kind of exaggerating this. And so now the combination, when we bond, is the combination of the LUMO from the diene and the HOMO of the dienophile, right? Flip from before. Before we had the HOMO of the diene and the LUMO of the dienophile, and here we flipped it. Okay, so now they're interacting in the opposite way. And it turns out that this leads to the same result. So the LUMO of the diene, again, we have p orbitals on all 4 atoms of our diene. And the LUMO looks like this. We have negative here, negative here, and then a node here, and a node here. So we have a node in between carbons 1 and 4, and 1 and 2, and 3 and 4, and then a constructive overlap between 2 and 3. So this is the LUMO, right? And now, let me put that somewhere because I don't need that space. And now let's compare it to the HOMO of the dienophile, the double bond. Well, that's just a complementary addition of 2 p orbitals that constructively overlap. Right? And they add together in the exact same way. Good. Okay. So this is why the Diels-Alder reaction always works thermally, because the HOMO and the LUMO on the end that we're adding the dienophile always symmetry matched, right? They're always matched either if we combine the HOMO and the LUMO of either one or vice versa. We either have a symmetric combination or an anti-symmetric combination. Either way, we get the right result. Right? So these combine to form the 6-member ring. So now let's compare this to the example that I showed earlier, which was the 2 plus 2, right? Add 2 double bonds together, and that didn't work. Right. So counterexample. Well, it's not really a counterexample, but if we take an electron donating group on 1 and add it to another double bond with another electron withdrawing group, right? And I said this doesn't go. And again, if we have a donating group, that means that the HOMO is high energy for this one, and the LUMO is up here. This is the EDG one. And then this one is a withdrawing group, which brings the LUMO and the HOMO down like this. Okay, so the combination of the frontier orbitals that's going to cause this reaction is going to be this HOMO with this LUMO. Right, this is the bonding combination we're going to make. And so let's look at the molecular orbitals for those, but maybe you can already tell this is not going to work because the HOMO, again, have a symmetric combination of orbitals. So they're positive on one side and positive on the other side. And then the LUMO of the other group, this one, again has opposite, it's anti-symmetric combination. Right? So now you have a clash. Right? This does not match, and this does. Okay, so this doesn't go at all. Now, if you're lucky, you can actually get it to go because there's an interesting point. Let me redraw this. So it can't come in the same way that it does in Diels-Alder, right? So the idea is that this adds to the same face of the other one, right? But this doesn't match with this. This matches, but this doesn't. So it can't come in and add to the same face like the Diels-Alder reaction does. But you might notice that this can go, even though this can't go here, it can go here, and this matches here. Right? So you can form a twisted system. So this might form something that looks like this. Let's see if I can draw this. A structure that looks like this instead, with a double bond here on the back side. Okay, and that's where the LUMO adds across the face. this goes, well, actually, let me do it the other way. I apologize. This goes here, and this goes there, right, above the face of the plane of the molecule. So one bonds to the bottom part, and the other one bonds to the top. So this is kind of like a twisted cyclobutene. Right, so this could be thermally allowed, but this is highly unstable. Falls apart back to reactants. So there's an EWG here and an EDG. Is that right? Yeah, EDG here, for instance. Right, that's where it's twisted. It's not, even though it's allowed, the barrier to get to this structure is it's high, and also it's not very stable, and so the equilibrium lies towards here. Right? So the end result is that this reaction to form a regular cyclobutene, where you have a withdrawing group here, and maybe a donating group here. This is no good. This would be the natural structure that you would form where everything's planar, everything's normal. But you can form, in very, very, very small quantities, so I'm going to put an equilibrium error like this, a twisted form. Oh boy, let's see if I can do this. Something that looks like this. Like that. Ooh, that's tough. Where the system is twisted in and out of the plane. I'll draw another picture of it. Something like this. Right? But that's so strict, that's so flop, that's such a miserable structure that it's just going to isomerize and go backwards to that. Right? There's nothing stopping it from going backwards. So this prefers the reaction. So in general, this reaction doesn't go at all thermally. Okay, so there must be something. So the interesting thing here is that when I'm adding 2 pi electrons to this system, to an electron with 4 pi, it works fine. All the symmetries work out perfectly. No matter if there's which HOMOs and LUMOs are interacting, this 4+2 addition always goes. Right? All the orbitals are exactly aligned the way you want them to. And in this 2+2 case, it doesn't go. Okay? And the rule is very simple. And this is and in fact, you can predict a whole series of reactions that are increasingly more and more complex with these rules. The idea is that for cycloadditions, right, where you add 2 systems together to form a cyclic molecule, like Diels-Alder, those with 4n plus 2 pi electrons, so that is n equals 6, and what's the next one? 10, and then 14, are thermally allowed. And those with 4n, so that's n equals 4, 8, etc. So and 4, 8 or 12 pi electrons are thermally forbidden. And this is entirely general. And the reason why is that when you have 4n plus 2 pi electrons, so we have 4 plus 2 here, that's 6, you always get the right matching between the HOMO and the LUMO. They always symmetry match. You always conserve the symmetry of the transition state, right? You don't have to change anything. Right? Everything adds together in a logical way. But when you have 4 in electrons, like we have here, where we have 4, where n is 1, you always have a mismatch on your lobes. Right? So the only way for the system to add is to do it across the face like this. And typically that doesn't go because it leads to a strange structure. And so in terms of equilibrium, it's always going to go back to the reactants. So this idea of adding a double bond to another double bond on the same face, like we do with Diels-Alder, only works when there are 4n plus 2 total electrons. Okay? And that's because of this. Because otherwise, if it's 4n, you're always going to have a mismatch in the phases or the signs of the molecular orbitals in the HOMO and the LUMO. And in 4n plus 2, they always match up properly. Right? And might not come to us, might not be that surprising, because this is also, right, the same rules as aromaticity and anti-aromaticity. Right? If you have a 4n plus 2, the transition state of this system is 6 pi orbitals adding together with 6 pi electrons. That's aromatic, right? So this transition state is stabilized because it's an aromatic transition state. So it's fast and stable. And the transition state for a reaction of 4n electrons is anti-aromatic. And that's going to be destabilized. Right? So there's different ways to think about it. But the point that I wanted, and the thing that was so novel about this from Hoffman and Woodward was that they identified that in order for these systems to be thermally accessible, right, these additions and rearrangements and so on to be allowed without using light, there's a reaction is that you need to match the symmetries, right? That the orbitals need to be basically the same sign where they connect. Right? And that only happens in these systems that have 4n plus 2 pi electrons in this way. Right? So for instance, Diels-Alder is a 4 plus 2, right? 6 total, and that's thermally allowed. But two ethylenes together is 2 plus 2, that's 4, and that's not allowed thermally. Now what I want to mention is I mentioned before that if we took this system, oh, there goes my shoe. If we took the 2 plus 2 addition and then excited it with light, that it goes. So let's look at that for just a second, and it'll make sense very clearly why doesn't really matter which way I do this. When we add UV light, this gives me the product that I would expect from the addition. Not clear where that electron withdrawing group can go to either side, but just as an example, it could go there. And the idea is, again, let's do the diagram. The electron withdrawing group brings the LUMO down for this molecule. And the electron donating group brings up the energy of the HOMO. Now what I'm going to do is excite one of the molecules with UV light. Right? It doesn't matter which one I do. But what that's going to do is excite one of the electrons from the HOMO into the LUMO. All right, so let's just pick one. Let's say this one gets excited on the left. Right, so now I have this. Maybe it doesn't matter which way it is. Let's go down. So it's singlet. Something like this. So it's excited. But now what's happening is that now this has an electron in it, so now it's our new HOMO. Okay, so this is going to interact with this LUMO, the empty LUMO right here. Instead of it interacting with this HOMO, it's going to now interact with this LUMO instead. Right? So if we didn't excite, I'll just start that over again. Let me just repeat that. If we didn't excite the molecule, the bonding combination we're going to make is this one. Like that. That's a HOMO to a LUMO. But when we excite the molecule and put an electron here instead, now what we're going to do is combine with the LUMO of the other one. Because now this is the HOMO because it's got an electron in it, and this is the new LUMO, right? It doesn't have any electrons in it. But the symmetry of this orbital is a LUMO, right? So it's an antibonding combination. This is still a pi star, and this is a pi. So if I were to draw this, our electron withdrawing, electron pour double bond is going to look like a LUMO, antibonding orbital. That's its HOMO. So that's our new HOMO. That's excited. And then our electron donating, our acceptor, if you will. Actually, it's our donor because it's one of the, well, actually, it's an acceptor, I guess. Looks like this instead. It also has a pi star as well. Right, and they can add together constructively. Right, so this is good. Right, so 2 plus 2 systems can combine exactly the way Diels-Alder works. But what you have to do is you have to make sure that the symmetries of the two orbitals you're combining are the same. Right, so that requires you to take an electron from the HOMO excited to the LUMO with a photon, and then it can interact with the LUMO of the other molecule, and now we have the same symmetry on both sides, and it can interact. Right? There's a constructive overlap. Right? It's not hard to show if you look at Diels-Alder and you excite the diene up to a higher level, just like we do here, the reaction doesn't go anywhere. Because now the symmetry of the two, the HOMO and the LUMO you're combining are mismatched, and they don't combine. So additions with 4n plus 2 pi electrons are thermally allowed, but electromagnetically forbidden. And those with 4n electrons are thermally forbidden, but electronically allowed. All right, and that's just due to this conservation of orbital symmetry. This idea that when you combine the HOMO and the LUMO of two species together, that the product has to exhibit the same symmetry in the end. And so that only happens when the lobes are aligned. So orbital symmetry conservation means lobes of donor or acceptor and acceptor are aligned correctly. Okay, and this was the big insight of Hoffman and Woodward. Right? That you can explain all of these different types of reactions by just realizing that when you combine your two molecules together, either the LUMO of one, the HOMO of the other, or vice versa, that the symmetries need to be aligned, they need to be conserved, and that everything can overlap constructively, right? And that simplifies basically for additions to this rule, right? That 4n plus 2 pi electrons are thermally allowed to add together, 4n or not. Right? There's an aromatic one and an anti-aromatic combination. And again, I don't have to do any math, right? All I have to do is calculate my LUMO, my orbitals, right, with Hubble theory. I'm not doing any math here. Just, you can reconstruct all of this by just building little Hubble and molecular orbitals, with your little matrices and calculating the eigenvectors for these systems. Plot them, and you'll see that they don't match up, right? Very simple analysis. Okay. Any questions about that so far? Okay. So I want to show you some more interesting examples of this behavior. You can predict entire multiple classes of reactions this way. Maybe I'll do it over here instead. Not just cycloadditions as well, but let's look at them a little bit. So let's look at it. Let's look at an interesting reaction. What I'm going to do is I'm going to take cyclopentadiene. I'm going to take 2 of them. Right? And I'm going to react it with heat. And the product that you get is very interesting. Like this. All right, you take cyclopentadiene and you heat it and it polymerizes, it dimerizes rapidly. I wouldn't say rapidly. This probably takes like a week under heat to do, but it does happen. And the question is why does it react this way? All right, and so what we're going to do is look at the orbitals of this molecule, and we should see that these should add in exactly the way that predicts this. Okay. Now the question is what is this bicyclic form, right? Where does all this come from? And it's actually quite easy to see once you draw it. So what I'm going to do is, because our diene and our dienophile, so there's 2 options. Let me just put it this way. There's 2 ways to react this, right? You might think, let me draw it this way instead. So here's my molecules. I'm putting them face on. And the idea is that you react in a concerted way like this, just kind of throw those things around. And the way what this ends up looking like is really frightening, actually. So you get so this right here, we'll call that 1. That's this little peak right here. And we'll call this carbon 2. That actually goes down like this, like that, and then we have a double bond here, like this. Okay, so that's one way this can react. Right? These right here are quaternary carbons. They don't have any hydrogens on them. Plus H2. We lose H2 from this. But this is forbidden because it's 8 pi electrons. This is a 4 plus 4 addition, which is 8, which is thermally forbidden. All right, so this doesn't happen. So there's only one way that this molecule can combine with itself, is that if you take the diene and then react it to one side of the molecule. All right, so that would be a 4 plus 2. That's 6 pi electrons, and that should be allowed. So let's look at that. All right, so what I'm going to do, and it doesn't matter which LUMO or HOMO I pick, you get the same answer. So let's look at the diene LUMO. Okay, so I'm going to draw it like this. I want to stick this terminal hydrogen up in the air, like so. So it's sticking out of the board. And then we have p orbitals here. All right, and it's the LUMO. So this is going to be negative, this is negative, and these are positive. Like so. And then our dienophile, we're going to look at the HOMO of it, is just one of the double bonds of the a pair of p orbitals on the cyclopentadiene. So let me draw the HOMO of this molecule. Let me draw a little bigger, sorry. So there's my dienophile HOMO. And we're going to have positive, positive, negative, and negative, like this. All right, and so how can these combine? Well, remember, we need to match the orbital symmetry. And so if we add, for instance, if we add this one and this one, for instance, imagine that this one goes underneath the system here, and this one goes underneath here, we'll see that they're not matched, right? Because this one, basically the top will interact with the bottom here, and the top of this one will interact with the bottom of this one. And this is positive, positive, negative, or negative, positive, and this one is positive, positive, so it doesn't work, right? So it can't add along this bond like this. If it did, you would get a structure that looks like this. It would look, let's see if I can draw it. Something like that. Where this double bond is sitting right here instead. All right, but that doesn't work. The reason why that doesn't work is because this combination where we put this bond right here, the one on the back, up to these two lobes here, they're mismatched in terms of symmetry. So that doesn't work. Right? So what is the combination of these orbitals that I can combine? Well, I have on the bottom face or the top face, I have matching here, negative, negative, so we want to add a symmetric combination of orbitals to it. Right, we want positive on the tops and positives on the bottoms or whatever. And so that would mean that this could come in here, we have positive, positive, and this one can come in here. Right, so instead of adding this face, the one that's opposite of the little sp3 carbon at the top, the little tip of our pentagon, we're going to add to the side of it instead, because that's the one that's symmetry matched. Right, so we have a plus here, a plus here, a plus here, and a plus here. Right, so those add up nicely. Right, so it's going to add across this face instead of this face. Right, so that leads to a structure that looks like this. Where the double bond is now formed on the far end instead. I might miss this one right here as well, like that. All right, so this is thermally forbidden. This first one across the, what are we going to call this face? 1, 2, 3, 4, 5. We'll label it like that. So this is across, so the thermally forbidden across 1,2 face, the 1,2 face of the diene. But addition, thermally allowed addition, happens across either the 3,2 or the 1,5 face, whichever one you want to pick. It doesn't matter. Right? And so that leads to that structure instead. Okay, and again, the only reason how I predicted that is I just matched slopes, right? That these are going to come in together along the same face of the molecule, right? Nothing's twisting or contorting at all. We're just naturally bringing it in, and so we're going to we need to find a pair of orbitals that constructively overlap with a pair of orbitals on the dienophile, and the only options are either this one or this one, right? They're symmetric, but across the bond they're antisymmetric. Right, so that means that the only way this can combine is along the side faces, not the face on the other end of the little tip, the 1, 2. Is that right? Yeah, 1, 2. Right, so again, all I have to do is just draw my HOMO and my LUMO and just match up symmetry configurations. So this, I don't know if this seems simple or complicated, but it's kind of amazing. These reactions have been known for a long time, and no one was able to explain them until the 1970s. And they're just like, well, let's just do very simple molecular orbital theory, and this all matches up very nicely. Okay, so that means then I'll just to summarize. This is allowed. So we'll say 100% of this plus 0% of this one. Okay, because this one is symmetry forbidden. Right? They don't match up. The orbitals don't match up in the HOMO and the LUMO. Now if I were to excite the molecule, if I were to excite one of the species with a photon, then this would flip. Well, it wouldn't flip because you'd excite both of them and then it would do the same thing. But if you had two different cyclopentadienes with different absorptions, then you could create this one if you excited one with a UV photon. In the same way that we could do the 2 plus 2. Okay. I have a couple more examples. This one I really like. This is a classic. I'm going to take my cyclopentadiene again. I'm going to react it with a different molecule this time. I'm going to react it with this Michael acceptor. I don't know what you would call that. Vinyl methyl ester. I don't know. Vinyl acetate. Methyl, something like vinyl formate. I'm not sure. Vinyl acetate, I think. Looks a lot like a choline, but it has an OMe, an ester instead. So this group we can think of as a double bond with an electron withdrawing group on it. All right, this is a strong electron withdrawing group. I'll just confirm that for you. We can do a resonance structure of this molecule. You have a resonance structure that pulls the electrons towards the oxygen, and that leads to electron withdrawing. That's just effectively electron withdrawing. Right? The oxygen, the double bond oxygen, is a pi base, and the pi acid accepts electron density towards it. Right? Pulls electrons away from the double bond. Okay, and so when you react these two, this reaction goes readily. Again, it's a 4 plus 2. Goes readily with heat. Gibbs-Alder reaction. But you get a mixture of products. The one product for the H is sticking above the ring, and the other product is the opposite. Where the CO2Me methyl ester group is picking out, and this is negative. So you get a mixture of products. I forgot the double bond here, sorry. And then if you measure the relative abundance of these two, without any changes, this is 90% and this is 10%. Right? So you form 9-to-1. This one on the left, where the methyl group or the ester group is pointing, is kind of below the ring, below the ring system. All right, the question is why is this? Right? You can use molecular orbital theory to explain this. And so what I'm going to do is do the exact same analysis that we did before. I'm going to take the LUMO of this, and the LUMO of this and the HOMO of this, and look at the two orientations where this ester group is coming from above and coming from below. Okay, so let's look at that really carefully. So let's start. So I'll give you these names. This is called an endo form, and this is called an exo form. All right, so let's look at how the endo form forms and the exo form. Okay, so let's use the LUMO. Just for simplicity, let's use the LUMO and the HOMO of this. It doesn't matter which ones we use. They'll both work. But I think it's a little easier to see here. So I'll draw my ring like this. So Again, I have a double bond here and here. Let me draw that a little cleaner. Sorry. Okay. I kind of want to show that it's sticking kind of out of the board a little bit, kind of sideways. This is a double bond. Like so. Okay, and let's draw the LUMO for this. So we have a p orbital here, a p orbital here, a p orbital here, and a p orbital here. And the LUMO for a butadiene has negative, just as we saw before, negative here, negative here. They're matched, and these are anti-matched. Like that. Let me draw that a little more cleanly. All right, so this is my LUMO. And then the HOMO of my dienophile so there's my double bond. The HOMO has matching orbitals on the double bond. And then where does then the question is again, we have a substituent on there, this ester group. And so if the ester group is formed below the ring in the endoform, then that means it's pointed this way, like so. I'll draw my double bond oxygen here, O-M-E, like so. And of course, this is also there's also pi orbitals here in the CO group. This is a double bond, so it also has a series of p orbitals that are conjugated with the system. And they're all phase matched effectively, like that. Sorry, no, they're not. I apologize. This one is opposite. Like so. Right, and so what happens when this molecule attacks? Well, remember, it wants to add on the same side of the face, and we're going to add this double bond to this diene. So this goes here, and this goes here. But the interesting thing is that I have this flipped. I apologize. This is actually, for this one, these are phase matched, and these are opposite for the HOMO. Notice that when this starts to come in through the bottom, and again, this methyl group is below the ring, so it's kind of pointed under the ring like this. Not the methyl group, but the ester group kind of pointed this way. That there's an additional interaction between these two as well as it starts to come in. This one is phase matched with this one, right? And so that helps to bring the system, right? This is a stabilizing interaction. There's an additional minor symmetry allows interaction between the HOMO and the LUMO. That lowers so let me write this in a straight line. I apologize. This is a stabilizing interaction that lowers the energy of the transition state. So as this dienophile attacks the diene, you can kind of help lock the system into place because there's this positive interaction between this lobe back here and this atom as well. And if you can justify by flipping it the other way, this carbon lobe right here will interact with this one instead. It doesn't matter which way you do it. This molecule is symmetric, and so either it's going to interact with this back one or this forward one. However, let's look at the exoform instead. The same analysis. All right, so here's my diene. I'll draw my orbitals in green this time. I'm kind of on the corner here. And I'll draw them with the same colors as before, same signs, just to keep it simple. This is positive and this is positive. And then let's add the HOMO of the dienophile. Here's our double bond. And now in the exoform, the methyl group is pointing away from the ring. Right? So instead of it pointing this way, it points this way. Right? So if I now draw my orbitals, let me draw them in green instead, sorry. HOMO for this is opposite phase, like this. Like that. Well, now again we have a same face syn addition of those two double bonds. The double bond, the dienophile is the diene, but now this is too far away, right? The other one is too far away, right? This group is too far away from these orbitals, so there's no interaction, no secondary interaction. Right? There's not this additional constructive combination of this orbital with this orbital, because now it's facing the opposite direction. And so this means that this transition state is higher energy. Because it's not stabilized, there's an additional partial bond, if you will, partial stabilizing additional combination there that isn't here. So transition state here is higher energy because it's less stabilized, and therefore it forms more slowly. Slower formation. And so that's why this reaction always leads to this product, the vast majority of it at room temperature, because of this additional interaction here that's geometrically allowed by having this orientation. And in general, these reactions conserve this kind of property, right? That the system wants to, in general, deals all the reactions prefer substituted systems to attack the diene from below the ring. Okay, so when you attack from below the ring, the CO bond, which has, again, pi orbitals, can interact constructively, but when you have it the other way, they can't interact anymore. So this is less stable. Okay. Yeah, so that's kind of all I have on this one. So again, the take-home point again is that if you can draw your HOMO and your LUMO for your system, and again, these are all very simple hydrocarbons, you can do the Huckel MO of this. We'll talk maybe again, it's a little tricky to analyze this because of the CO bond, but you can do it. Basically, there's going to be an alpha for this carbon, an alpha for this one, and a different set of alphas for these because they're in kind of different environments. Right, so you can still do a Huckel analysis of this, but you got to change your alpha for this oxygen, and the beta for these are different too than this one. Right, so you have to change your numbers a little bit, but you can calculate MOs for this very easily of Huckel theory, and of course this one's really, really straightforward. Right, you have the same alpha for all the atoms and the same beta for all the bonds. This atom does not contribute. This is just a substituent group. It doesn't contribute to the pi system because this is sp3. There's no p orbitals in it, so we don't really care about that one. So it's really easy to calculate the HOMO and LUMO of Huckel theory for this one, and it just needs a little bit of work for this one. And by doing that, you can predict everything precisely about these reactions, right? There are many different types of these reactions, different types of selectivities, stereochemistry and stuff, and all of the analysis is done with this orbital theory, HOMOs and LUMOs, right? If you know the HOMO and you know the LUMO of something, you can predict any reaction between the two up to a certain amount. All right, and this is, again, this goes much deeper. There's lots of different types of reactions that Hoffman and Woodward considered besides cycloadditions. Unfortunately, I don't have the time to talk about all of them. But the analysis is exactly the same. You identify an empty LUMO on one species, a full HOMO on the other species, and look at how those orbitals combine geometrically. And if they don't match up, then they don't match up, and the reaction doesn't go. But if they match up really well, if you can find a way to geometrically align them so they overlap exactly, then the reaction will go, and 99% of the time, that qualitative prediction is the truth. All right, so it's a really, really powerful theory of MOs, and this is where organic chemists really use MOs a lot because it helps them, right? How else would you predict these things without being able to draw these, right? Otherwise, you're just kind of pulling at strings. Okay, well, that's it. 2 semesters done. Thank you all for your hard work. I'll have some practice problems for next week for Sean on molecular orbital theory. Again, the exam will just be MO theory, mostly just Huckel stuff. I don't think we'll get too complicated into these reaction things. If I do have a reaction question, they'll be kind of straightforward and simple. I don't expect it to be too difficult. And I'll make sure you have plenty of practice too. And thank you all. I had a good year. I'll see some of you in the fall, of course. The rest of you, best of luck. If you need anything from me, anytime, recommendations, or some tips or some advice, whatever, you're welcome to email me. And thanks for your attention. Have a lovely weekend.
Every weekend. I'll send the chemistry. I don't know what to do.